show you how to do how to find the eigenvalues of a 3 by 3 with Matlab with a step-by-step process that you could potentially do by hand as well, and then with a function that just does it all for you. So let's go into Matlab and let me show you how to do this. Okay, so here we have the matrix that we want to define a matrix, and so that's going to be our matrix A, which is that 3 by 3 that you saw. It was 5, -1, and 0, and 0, -5, and 9, and 5, -1, and 0. All right, and now what we want to do is we want to find the eigenvalue. So remembering where the formula comes from, we'll define a new matrix. But first we'll define some symbols. Defining a symbol, actually. A symbol for lambda. Lambda here. And then we're going to define a new matrix, which is going to be the matrix A1. Defining a new matrix is going to be the matrix A1, and that's going to be equal to that original matrix. So I'm just going to copy it right here, copy, paste, but I'm going to subtract from this lambda, from this lambda, and one more time from this lambda. Okay, then I'm going to ask computing the determinant of this matrix. I'm going to find that that's going to be the determinant of A1, and then I want to see what happens. So we get that the determinant is equal to this. Now I want to find the roots of that. Finding the roots of the determinant, we could just factor out lambda, and we'd see that we'd have a lambda equals 0, which means that this determinant is singular, non-invertible. And then we'd have 16 minus lambda squared, which means that lambda is equal to plus or minus 4. So we should have plus 4, minus 4, and 0 as the eigenvalues of this matrix. But one way to find the roots, you may have a more complicated version of this, is to write those roots in order, from ascending order. So the third order is the highest and has a coefficient of -1. The second order has a coefficient of 0. The first order has a coefficient of 16. And the 0th order has a coefficient of 0. If I do this, oh, maybe I have to do this. When calling a function, use parentheses. My bad. And so now we get this, Control Enter, and we got the solutions that we were expecting. So if you had something more complicated, you could use this roots, and that would give you the roots of the polynomial. But you have to remember that you have to start from the highest and then go down by 1, put 0 when you don't have a term, and include the 0-degree term. Then, now that we know our eigenvalues, I can define, for example, the A0 if I input 0, and that's going to give me this matrix right here. It's going to give me the matrix. Control copy. I'm going to paste this, and now I'm going to subtract 0. So basically it's just going to stay like it is. And what I want to do with this is I want to augment it and have it that each row is equal to 0, to the 0 vector entry corresponding to that row. So now that I have this, and I'm going to say augmenting the matrix for lambda equals 0. I'm gonna find the eigenvector with RREF. So RREF of A0 is gonna give me my K1, my first vector. And if I do that, I'm gonna show you that here we have our identity matrix, and then we have to solve for this. So then we know that we'd know that x is for x plus negative 9 over 25, z equals 0. And then we'd have to solve for x and y and z, because in this case we have 3. And then we do the same process for the other two values. So let me do the value of 4. I'll use the same template here, and I'll just change some values out. So that's going to be 4 here. And now if I had subtracted 4, 5 minus 4 is 1. Then negative 5 minus 4 is negative 9. And 0 minus 4 is negative 4. And now we'd have this. And then I would do it one more time. This would be K2. And this would be K3. And this would be minus 4. I don't think I can name it like that, so I'll name it this. And then that'd be like adding 4. So this would be negative 1. And this would be 4. And this would be this. So then we'd have a K1, a K2, and a K3. As you see, they all have a row that equals 0. And then we'd have to solve. Now, let's do the second way, which is using the built-in Jordan function. If you use a built-in Jordan function, what we have to do is we just have to assign an output for the vector and the values that it gives us, and then input the original A, this one right here. Then we press Control Enter, and what we get is the 3 values, 0, 4, and the negative 4, and we get what we got over here for the other values. Now this looks slightly different because this is not the matrices here, the augmented matrices. These are the vectors themselves. So if we were to solve these 3, now if we were to write them back as x minus 9 over 25z equals 0, and y minus 9 over 5z equals 0, and solve, we would get this, then this, and then this. So this is a very powerful tool because it saves a lot of time. Look at how many steps we had to do here, and we weren't even done. We still need paper and pencil to actually finish it. Well, this one did it all in one step. So it's a useful tool as long as you understand how to use it. And I hope this was instructive, and I'll see you next time.